Hello everyone again. This is lecture number 5 from Work, Energy and Power Concept. In the previous lecture, in this lecture series, we have started with the discussion about the concept of potential energy. So, let's move forward from that. A little bit discussion more is required regarding that, and then we can move on to the next concept. So, this is lecture 5 from Work, Energy and Power. I'm Samir Lawankar. Let's begin our discussion. So, currently, a little bit course outline for you before starting the complete discussion. So we have completed, or currently we are on the seventh topic, that is the concept of potential energy. We have started with the introduction, in which we basically understood a new concept of vector, which was called as dot product. Just a quick revision of what is dot product. So dot product is basically denoted as vector A dot B is nothing but equal to magnitude of A multiplied by the magnitude of B multiplied by the angle between them, the cos of the angle between them basically. Okay. So this is a scalar quantity, please remember. And this is also called as scalar vector product. Scalar vector product. Fine. The next thing is about the notions of work and kinetic energy, the work energy theorem, in which we basically understood that the change in kinetic energy is nothing but equal to the work done. So basically, a cross product of force and displacement. Fine. The next thing we understood about work. So basically, what we understood that F dot T is nothing but equal to F cos theta. Is basically equal to, sorry, not F cos theta, it's Ft cos theta. Correct. And kinetic energy, we understood that kinetic energy is nothing but equal to half multiplied with the mass multiplied with the square of the velocity. And next concept, so till all these four concepts, the concept of understanding of force was assumed as constant force. Okay. In the fifth concept, we understood force, which was a function of x. Okay. And then we understood that how the work done is being done by variable force. And then we understood the integration part of work energy theorem for the variable force. That thing being said, in the last lecture, we understood the potential energy. The potential energy is denoted as V of x, which is nothing but equal to, for gravitational force. We're talking about gravitational force only, it's equal to mg into h, where h is the height. Okay. Then a little bit more discussion was being explained regarding conservative force and non-conservative force. So conservative force, so basically a force for which the complete work done, let's say in a complete loop, or is zero, and another was basically your non-conservative force. Non-conservative force. So non-conservative force, we can take the example which is dissipative force. All the dissipative forces comes into it. All the dissipative forces comes under this. Such as example is your friction. Okay, so these are concepts were being understood in the past few lectures. So today, let us first complete the seventh point, and then we can move on to one of the most important topics. It is basically a fact which we will even consider in future understanding of physics in the subsequent chapters. So that is the conservation. It's conservation of mechanical energy. Right. So that thing being said, just quick revision is being done. Now let us move on to the original concept. So we started with the concept of potential energy in the previous lecture. So these all things are completed. Let's move on. So finally, what we got, that the gravitational potential energy of an object can be denoted as V of h. It is nothing but equal to the force, that is mg, multiplied with the height, that is mgh. Okay. So the amount of work done is basically for the amount of work done against the gravitational force. So let me write also. So the amount of work done against the gravitational force, to raise an object of mass m to a height h is basically m multiplied by g multiplied by h, and that is your potential energy. Fine. Then after these all things being said, we equated basically that half mv square is equal to mga. So basically what happens is, let us say we have a ball here, correct? Or let us understand it like this. Let us say this is your ground surface, and let us take some ball and keep it at height h. Then let us drop this ball from here. Okay, so what happens is that amount of energy which it has at this moment, at this location, is nothing but equal to mgh, right? As it keeps on going downwards, the potential energy, let me know the potential energy is v of x, is keep on decreasing. But if you look closely, it's an example of a free fall, correct? What happens in free fall? Due to the gravitational force acting on the ball, the velocity of the ball keeps on increasing. So, in other words, what we can say that the kinetic energy of the ball, is increasing. Why? Because the velocity is increasing. Okay. So therefore, let us suppose that the amount of energy which was here is the velocity with which it hits the ground is v. Therefore, the kinetic energy is basically half mv square. Okay. So what happened actually? The amount of potential energy which it had in the initial phase is being converted completely into kinetic energy. You can say clearly from the location also that the potential energy here is nothing but equal to 0. Fine. So these all things are considered. And finally, I think the last concept which we consider or explained was for a variable force. For a variable force, we understood that we can write that the change in potential energy is nothing but equal to integration being done from xi to xf at h dx. Okay. We also understood about the conservative forces. What are basically conservative forces? A conservative force is a force with the property that the total work done in moving a particle between the 2 points is independent of the path taken. Okay, so it basically depends upon your displacement. Okay. We also understood the dimensions of it. So when we calculated dimension, we found that the dimensions of potential energy and kinetic energy both are same, which is equal to ml2 t minus 2. The dimensions of kinetic energy is also this. Okay. That thing being said, now let us understand this last 3 lines and then we can move on to the next ones. Okay. So to reiterate, the change in potential energy. How can we denote change in potential energy? We know that we have understood a symbol called as delta. The change in potential energy, that is change in delta V for a conservative force is equal to the negative of the work done by the force. Okay, so what is the negative of the work done? It's negative. What was the force? Please remember we were talking about the variable force here. So it's Fx and it's work done correctly. So what is work done? Work done is force into displacement. So because we are talking about delta value of displacement, therefore we will write delta value of x also. Okay, so what is the relation we got? That delta v is nothing but equal to minus f delta. This is similar to this case scenario only, but the only thing is that we are talking about the complete integral here, but here we are only talking about a small integral or basically a differential form. Okay, moving on. So in the example of the falling ball considered in this section, we saw how potential energy was converted to kinetic energy. So I just did a revision for this here. If the diagram is still there, yes. So this was the example we explained, as in the ball was at the topwards previously at the initial phase, and then it moved on to the next phase, which was regarding your kinetic energy being changed. So basically it was at 0 value of kinetic energy first, and then it changed to find a maximum value of kinetic energy when it was at the ground. Fine. So I guess that thing is explained now. Moving on to the next thing. So this hints at an important principle of conservation in the mechanics, which will be understood now. Okay, so basically what is happening, let me not disclose anything till now, so it's a very good example which you will understand in the next time. So something of conservation is happening, something is getting conserved. There is no what we can say evolvement of any new thing. There is no movement of anything. There is no disruption happening. There is no destroying of anything happening. There is some sort of conversion happening between two different things, or some sort of thing, or some, let's say some energy is only being changed into another form. There is no new form of energy being created, and that is the main basic principle regarding the next concept which we will start, which is the conservation of mechanical energy. Okay, so let us understand the conservation of mechanical energy. Okay, so I will go very slowly. Very small concept, very easy concept, but it's a universal concept which we need to remember. Okay, fine. So for simplicity, we demonstrate this important principle for one-dimensional motion. Let's start with one-dimensional motion only. Then if the things persist, we will go on with the other dimensions also. Okay. Suppose that a body undergoes displacement delta x under the action of a conservative force F. Okay, so let us understand this some sort of like this. Let us say there is a ball, or let's not take a ball, let's take a normal object. Let us take this object. Okay, and it is, as we are talking only about one dimension, so let us take this force to be in this direction. Let me write this force as f of x here, correct, because it's a variable force, and we need to calculate the work done. So what will be work done? So work done will be nothing but equal to, so here we are writing work done as delta K, but it is delta K only. So that delta K is nothing but equal to this force multiplied by delta x. So no difference in this. Okay, so even if you do the dot product and find the angle between them, as the angle between the displacement and the force is same, or angle is 0, therefore cos 0 is 1. So in that way also the answer would come same. Okay, please remember, it's a very important point here. The force considered is a conservative. Okay, this is very important. So then from the work energy theorem, we have what we have, delta K is nothing but equal to f of x delta x. Okay, if this force is conservative, okay, please see here. So if and only if the next line which you are trying to understand now is only and only implied when we are talking about the conservative forces. So for conservative forces, the potential energy, how we know potential energy? We know potential energy as V of x can be defined as, what can we say? We can directly say that delta V, we just understood it in the last point. No? The delta V is nothing but equal to minus f of x into delta x. Okay, so it's negative of the work done. Correct? And in other way, we can also write it as delta V is nothing but equal to f of x delta x. Correct? So just look at these two equations. So let us take this as equation number 1 and take this as equation number 2. So adding 1 and 2, adding equation 1 and 2, we get delta K plus delta V is equal to f of x delta x minus f of x delta x, which will give you answer as equal to 0. Right? So basically, the sum of the work done positive and the potential energy is basically equal to 0. Or in another sense, what we can write? We can also write this as equal to nothing but change in K plus V, because this is directly a summation. So delta can also be written like this. So what we got finally, we get a delta of K plus V is equal to 0. Or we can say that kinetic energy plus potential energy is a constant term. A very important discussion which we will understand more about in the next slide. Okay, so finally what we got was simple multiplication. Till now we are just doing this for a one-dimensional motion, but the thing per se, this is also valid for 2 dimensions and 3 dimensions also. Okay, so what does it mean? Just the final line which I just implied here. So it basically means that the K plus V is a constant. Okay, so which means that K plus V, what is K plus V? It is the sum of the kinetic and the potential energies of the body is a constant. Very important term. So it is constant. Okay. So over the whole path, xi to xl, what does it mean? It basically means, so basically as we return that delta of K plus delta of V is equal to 0. And what we wrote, that delta of K plus V is 0. That is That is, the kinetic energy plus the potential energy is a constant. So at any time when we take the potential and kinetic energy at any position x, we will always get it same. So let's say first I calculate for ith position, and then we calculate for some final position. So therefore this will be ki. We can write the potential energy at that point as nothing but P of xi, let us suppose. And similarly, what is at some final position? It's kf plus potential energy, which can be done as V of xi. So these both are same. Okay, and that is the equation which is given. Okay, so basically ki plus V of xi is equal to kf plus V of x. Okay, so I hope it is clear. Please keep remembering that we are doing this just right now for one-dimensional motion. Okay. So this quantity, which is K plus Vx, is nothing but the total mechanical energy of the system. Okay, so if you are being asked the total mechanical energy, let us say I make a question. Will not solve the complete question. I'm just making a question. Let us suppose a ball is given to you, which is going to hit the ground here. Some value of h is given to you. The value of velocity is also given to you, and let the velocity at this point is given to you. Let us suppose. Okay. And the mass is also given to you. And now the question is being asked to you that please tell the kinetic total mechanical energy of the system. Okay, so even if you calculate at this location, or you calculate directly at this location, or you calculate at any midpoint, or let us say they asked you only for at any value. Let's say at x is equal to 0.73 meters, they have asked you to calculate the value of total mechanical energy. Let us suppose this height is greater than this. Let us say this is 4 meters. Okay, so you won't be going to 0.73 calculating the velocity there. If you directly calculate the potential energy here, or you directly calculate the kinetic energy here, you can directly find the value of total mechanical energy. Okay, so that is the basic crux of what we are understanding here. So as the total mechanical energy of the system is always constant, as long as only and only, so let me just write it also. So constant as long as just give me 1 minute. As long as only conservative forces acting on the object, right? So that thing is being said. So I've explained you till now. We understood till now what is total mechanical energy of the system. Okay, so we understood what is the total mechanical energy of the system. Let's move on. So K plus Vx is nothing but your total mechanical energy of the system. Okay. Individually, the kinetic energy K and the potential energy V of x, so kinetic energy is K, potential energy is V of x, may vary from point to point, but the sum is constant. So just think which I explained to you. So the potential energy at this location, at this location, at this location, at this location will be different. Similarly, the kinetic energy at this location, this location, this location, and this location will be different. But the summation of kinetic energy and potential energy at each of these locations will be constant, which would be same. Okay. So the aptness of the term conservative force is now clear. So you can understand what is the basic crux of using a conservative force, or what is the power this conservative force holds. Okay, so this is very, very important concept when we understand future results such as rotation, such as collisions, etc. Okay, the use of conservative force there plays a major role in understanding the future concepts. Okay, the first concept which we started with was conservation of mechanical energy. Okay, so let's understand more about this. Okay. So till now what we know? We basically know that for a conservative force, the kinetic energy and potential energy at any location is a constant. Okay, let me write the constant as some K. Okay, but K can be a little bit confusing. Let me write it as constant. So moving on. So let us move on. Let us consider some of the definitions of a conservative force. Okay, so a force f of x is conservative. So when it is conservative, if it can be derived from a scalar quantity v of x by the relation this. Okay, so this was the first discussion we just had in the starting of this lecture. So it was one of the definition being given to either we can say for potential energy or we can say for conservative force. So what we got, that let us say we need to calculate, or what is basically delta V. Delta V is basically defined as negative of the work done in moving from or for covering for when an object is moved for a displacement delta x by a conservative force, by a conservative variable force f of x. Okay, so this is only and only possible for a conservative force. I guess this thing has been explained to you many times. Here also it has been explained. I think when we explain this, here also it has been explained. Okay, just keep remembering that this is only and only valid. This is only and only valid for a conservative force. Fine. Let's move on. So this was one of the definitions. Now the three-dimensional generalization requires the use of a vector derivative, which is outside the scope of our present study. Okay, so we won't go into the results of understanding what how to derive it for 2 and 3 dimensions. But you should know, you should remember that the conservation of mechanical energy is valid for both one or valid for all 1, 2, and 3 dimensions. Okay, deriving it right now is a little bit complex because many different properties are being used there. Different amount of calculus is also being used there. So we won't go into that detailing right now, but we can just remember it as a fact that the conservation of mechanical energy is applicable for even 1, 2, and 3 dimension. For 1 dimension, so we have already proved. It can be also proved for 2 and 3 dimension. Okay. Let's move on more. So the work done by the conservative force. Again, please remember, it is a very important concept here. We are only talking about the conservative forces here. Okay. So the work done by the conservative force depends only on the endpoints. That is the basic definition when we started understanding what conservative force is also. So we understood that thing there also. So this can be seen from the relation. How can we see it? So so basically what we did here, we knew that Ki plus V of xi is nothing but equal to Kf plus V of x. Just doing some mathematical modifications, we can get Kf minus Ki is nothing but equal to V of xf minus V of x. Correct? So what does it say? That the change in the final position and the initial position's kinetic energy is equal to change in the final and initial position's potential energy. Okay. So either let us say this is your position xi, and let us say this is your position xi. Correct? So let us say if I go from this location to this location like this, or I go in this fashion, or I go directly straight, or I go upwards, come down, go upwards, come down, any fashion. We do it any fashion, the path may be any way, what we want. The amount of kinetic energy and potential energy always depends only upon the final positions of kinetic and potential energy and initial positions kinetic and potential energy. Okay, and that is only and only valid for conservative force. Okay, let's move forward. So which depends only on the endpoints, which has been explained right now. Okay. A third definition that states that the work done by this force in a closed path is zero. So this was a definition I gave you in the starting when we were understanding the course outline. So basically it is just saying that let us start from this location. Let us say I start from this location. I go in a loop. I end up at the same location, and the complete work done will be nothing but equal to the amount of force which is being acted on into delta x. What is value of delta x? Delta x is zero. Therefore the answer should be equal to zero. Okay, so therefore the third definition states that the work done by this force in a closed path is zero. But it is not just certain that it should be in circle only, it can be any path. I go like this, wave like this, and end up here, or I go in a very zigzag pattern and then I end up here. Anyway, we are reaching at the same location, then the work done should be equal to zero for what? For conservative force. Fine. So this is again apparent from the equation. That is, again, we just use this equation only. So from this, if xi is equal to xf, so if I put xf in the place of xf, I put xi, then also it is valid. So basically the sum of kinetic energy and potential energy is equal to sum of the final energy and final potential energy and final kinetic energy. Okay. So this thing also holds till that point also. Fine. So moving on, let us understand more. So we are just defining everything. Thus, the principle of conservation of total mechanical energy can be stated as follows. Before understanding this, let me first again revise what is total mechanical energy. If in any question you have been asked to calculate total mechanical energy, what you will do? You will just find any position of x at which you can easily calculate the total mechanical energy over the complete path being given to you. So you will have some value of xi, you will have some value of xf. So using this value, using this complete path, you just need to find that value at which you can just calculate the kinetic energy plus potential energy. Okay, and that thing being done, you can have the answer. Okay. So that was just mathematical calculations and so on, which can be asked in exam. Currently, we're understanding the definition of conservation of total mechanical energy. So the principle of conservation of total mechanical energy can be stated as follows. That is, the total mechanical energy of a system is conserved. When it is conserved, if the forces doing work on it are conservative. Very, very important. So if, let us say, there is an object F, there's an object with a mass m which is having, let's say, force in this direction as f1. Let's say it is having some force in this direction, say f2. It is having some force in this direction, say f3, and it is having some, let's say, force in this direction, say f4. Okay, but all these forces are conservative. Then the way in which this this mass will go on at its initial location and its final location, the kinetic energy and the potential energy would be same. Okay, but if even one of this is not as a non-conservative force, then dissipation would occur. There will be leakages in current, there may be leakages in the energies, and then we cannot directly use conservation of mechanical energy. Okay. The next thing is the above discussion can be made more concrete by considering the example of a gravitational force once again and that of the spring force in the next section. Okay, so just an example again, we will understand a very beautiful concept after this, which is about the springs. We will understand about springs more, how the energy is being stored. That is a perfect example of understanding potential energy. So just a few minutes, then we can go with the discussion. Just understanding, making you understanding the gravitational force concept again. So we just took a ball, kept downwards to it, and let us see we calculate the value of velocity here. At the initial location, what is the total mechanical energy? Let me write total mechanical energy. Total mechanical energy at this location is nothing but mg into h. Here m is the mass, g is the gravitational force acting on it, and let us say this is the height h. Okay. When it reaches the ground, the value of the total mechanical energy is nothing but equal to half multiplied by m multiplied by v square. Okay, and let's say when to calculate at some this location, so what is total mechanical energy? Let us say this is at some h by 2 from the ground. So this will be equal to nothing but mgh by 2 plus half m v dash square. What does v dash square depend upon? It depends upon the value of the potential energy, value of the velocity at this location. How can we calculate it? Let us say this is in free fall, then we can just use the simple kinematics equation and calculate the value of velocity at this location. We can also use v square is nothing but equal to 2gh. Okay, 2gh, yes. Fine. So that thing being said again, so even if you calculate, so basically mgh is equal to this half mv square and is also equal to this mgh by 2 plus half mv dash square. So if you calculate correctly, you will get v dash square is nothing but equal to 2gh value, where h is nothing but h by 2, and you will if you just add it, you will get answer as mgh only. Or you convert this mgh into half mv square and then add it again, and then convert this v dash value also, you will get the answer also equal to half mv square. So basically, verification can also be done, but all in all, the conclusion is that this value is equal to this value is equal to this. Okay, fine. So I think that is the end. Okay, one more concept. Okay, so just thing which I explained to you is written more clearly here. So let us understand this thing here. So figure depicts a ball of mass m being dropped from cliff of height h. So basically this can be understood as a cliff here. So let us say this is a cliff here, which is having a height h. Okay, so the total mechanical energies. Let us say we calibrate three total mechanical energy. One is called as E0. Next is EH. And finally is E capital M. Okay, so what does E0 stands for? E0 stands for this location. What does E small h stands for? E small h stands for, let's say, this location, and what is E capital H stands for? E capital H stands for this location. For the second E small h, the E small h can be at any height, which is from lying between 0 to capital H. Okay, so the total mechanical energies, that is E0, EH, and capital H of the ball at the indicated heights, 0, H, and small capital H. Okay, so let us calculate first E capital H here. How will calculate E capital H? That is at this location. Because the velocity here is 0, therefore only and only potential energy would take place here. So it's mg into capital H. Okay, so I hope the equation number 1 is clear to you. Now let us calculate E small h. How will we calculate small h value? Sorry, E small h value. That will be nothing but the summation of potential energy, which is mg into small h plus half m. What is the velocity at that location? We can denote it as small vh squared. Okay, that is equation number 2. And similarly, what is E0? So at E0, you can clearly see that the value of potential energy should be equal to 0, but there would be some velocity of it because it's a free fall. So it's half into m into v capital H square. Okay, or we can write it as v final square. Okay, fine, and that is only been explained here. So this is your E capital H, this is your E small h, and this is your E0. Okay. The constant force is a special case of spatially dependent force f of x. Okay, so in this time we have understood this as constant force only. We can even work with a variable force. Okay, hence the mechanical energy is, so we know that as the mechanical energy is constant for a conservative force, so we can just equate both of these, right? So therefore we can get that mg capital H nothing but equal to half mvf square, and therefore using simple manipulations you can get vf is nothing but equal to root over 2gh. Okay, so I think this is clear. Even if it's not clear, I will do the mathematical calculation here. So it's mg into capital H is nothing but equal to half m vf square, right? Mm gets cancelled. Let me keep 2 in this direction. So it's vf squared is equal to 2gh. Therefore, vf is nothing but equal to root over 2gh. Okay, so that's how you got the value of vf as equal to 2gh. That thing being said, now, so this is a result that was obtained for a freely falling body. So I explained to you this again. I think 3-4 times this thing has been explained now. So let's move forward. Further, E capital H is equal to E small h. We know this thing also. So therefore, what we can do, we can just equate E capital H. So what was E capital H? It was this value. And what was E small h is for this value. So just equating both of them again. So because we know how can we equate both of them? We can equate them because the total mechanical energy remains conserved for when a conservative force is acting on it. And we know that gravitational force is a conservative force. Okay. So I'm just writing. So E capital H is nothing but equal to E small h. What is E capital H? E capital H is at this location. So it's M into G into capital H, which is equal to nothing but E small h is at this location. That is M into G into small h plus half into M into V small h squared. Okay, just keeping it in this direction, we can get M G bracket capital H minus small h is equal to half M VH squared. Getting cancelled, just keep this to this location. So you can get V small h is nothing but equal to V small h squared is nothing but equal to 2g capital H minus small h in bracket. Therefore, V small h is nothing but equal to under root of 2g into capital H minus small h. Okay, so that's how you can understand this concept from here. So what is the final conclusion? The final conclusion is simply this, that V small h is nothing but equal to under root of 2g into capital H minus small h. Fine. So that is the implication. Okay. And is a familiar result from kinematics. Okay. At the height capital H, the energy is purely potential. Okay. At the height capital H, the energy is purely potential. It is partially converted. So this is quite evident. We know that at this height it is purely potential. It is partially converted to kinetic at height h, and is fully kinetic at ground level. So this also you can understand, fully kinetic at ground level and partially converted or partially potential at some location, height small. Okay. So it's partially converted to kinetic energy at high h and is fully kinetic at ground. Okay. So this illustrates so some of the potential energy here is being converted to kinetic energy here. Okay. This illustrates the conservation of mechanical energy. Okay. So another way we can also say energy can neither be destroyed nor created. It can only be transformed from one form to another. Okay. So I'm writing that thing also here. So energy can neither be created nor destroyed. It can only change its form one source or one source to another. Okay, so that is one of the definition or just explanation that energy can neither be created nor destroyed. It can only be converted from or change its form from one force or one way into another. Okay, fine. So that was the complete explanation of conservation of mechanical energy. Now let us understand one of the example here. Okay, so this example is also this example is basically depending upon a bob, but please remember the concept or please remember the velocities. I highly suggest you to remember the velocity which we will be discussing in the coming slides. Okay, so this is also one of the discussions we generally happen. These are generally asked in exams also. So just try to understand this complete question very clearly and then let us move forward. Okay. So let me first explain what is the question being said here. So it is said that a bob of mass m. So what's a bob basically? A bob is basically a ball which has been tied to some wire. Okay. So a bob of mass m is suspended by a light string of length L. Okay. So what is the meaning of saying light string? So light string simply can be understood or assumed as the amount of mass which this string holds is negligible, or we can just remove or we can just assume the mass of light string to be zero. Okay. So a bob of mass m is suspended by a light string of length L. Right. So as you can see, it is being suspended from this location. This is the length L, and this is that bob of mass m. Okay. Right. Next thing is it is imparted a horizontal velocity v0 at the lowest point A such that it completes a semicircular trajectory in the vertical plane with the string becoming slack only on reaching the topmost point C. Okay, so what is written here? Let me explain to you. So it is just written that it is imparted a horizontal velocity v0 at the lowest point. Yes sir. Yes sir. Yes sir. जी सर. अच्छा ओके सर ओके. तो फिर उसमें नए लेक्चर चालू करूं. ठीक है मैं इसको ऐड करवा दूं. ठीक सर. अच्छा अच्छा ठीक है ओके सर. ठीक है. So let's continue this discussion in the next part of the lecture. So thank you so much. We will meet in the next lecture. So thank you so much.